Mr. Craig, does our copy also say?
It should say E6.
Okay. Oh,
Yeah.
no.
I don't understand why mine says E5, but it does. So I probably, yeah, no, doesn't matter. Okay, so there is this type of function that we refer to as an accumulation function. We have to make sure that a couple things are in place before we call something an accumulation function. So if you have a function which represents the rate of change of some quantity, this other function, which I'm identifying as capital F of x, which is the integral from a to x of the original function, that thing is called an accumulation function. So the things that we are looking for is we are verifying that our lower limit is a number. If the lower limit is a variable, if the lower limit is a function, then you do not have an accumulation function. You've got a function that does not have a special name, but it is not an accumulation function. The upper variable needs to be just a variable. It can't be 2x. You don't have an accumulation function if it says 2x. The letter does not matter. Commonly, and especially if you throw one of these in Desmos, you need to use a different variable inside of your integral, just because they are serving different purposes. The variable inside of an integral only lives inside of that integral. It's kind of like a dummy variable. We used that terminology a little bit when we were doing limits. You can change that t as long as you change it in both places to any other letter, and you have not changed anything except for which letter you're using. So this is kind of the normal setup of it. The function is a function that we are going to plug x into. So if I say the f of 3, that 3 is going here, not here. Let me do that again for the people watching the video. So if I say the capital F of 3, that 3 is going here, but not here, which is why we use the two different variables. Okay. An accumulation function does the same thing an integral does, because essentially we've just taken an integral with two numbers and let one of those numbers be a variable, the upper limit. It tells you how much the quantity has changed as a result of the rate between a fixed starting time and a variable ending time. Okay. All right, so example one, let's talk about what these mean in context. We'll have another context lesson coming up, but I think we'll be able to be able to chunk out 3 days for it. So that's a good thing. If you remember B11, was it B11 that everybody? Oh yeah, Joey remembers. B11, we've got an E something coming up that is B11's best friend. Yeah. But I'm going to go, B11 was the context question where we first really used Desmos to answer some questions, and it was all AP questions. We're going to have another one of those, but now that we know how to do integrals. But I think we're good to map 3 days out for it, which is probably what we needed for B11 as well. But we didn't. Okay, so anyway, with that being said, F is a function that represents the rate at which guests at an amusement park enter the line for a popular ride. So little f is a rate. It's the rate that people enter the line t hours after the amusement park opens. The variable a equals, and one change that I made here for simplicity's sake is 0. So just an update. After I was doing my notes on this morning, I want to make this one 0. So I'll do the first one for us, and then I'll start asking questions for letters C and B as they're numbered on your paper. What does that mean? Well, it's how much change has occurred as a result of that rate. So if it's the rate at which people are entering the line, it's telling us how many people actually entered the line between t equals 0 and whatever our variable x is. So we'll write that out. So this is the number of people who have entered the line This is not a standard AP question. I think it's important. It's not something you don't need to know, but it's not like a standard AP question where there's like a set format for answering it. Be careful when you are thinking about these things that you don't veer away from what it says. If you say that that function represents the number of people in line, you're incorrect, because some of those people that got in the line hopefully got on the ride. So those people aren't in line anymore. So you really, it kind of goes back to what I said when we are explaining these things. Use their words. If they said the rate at which people enter the line, then tell me the integral is the number of people who have entered the line. Cool. All right. So letter C, F says, and I changed the words, not that it really matters here, it just seemed silly to me with my variable here. Microsoft Word. I'm going to blame it on Word because I'm not really sure. Because when I looked at it this morning, I'm like, that's bizarro. I hate when Microsoft Word auto numbers stuff, but sometimes it's just unavoidable. Like you argue with it 3 times and it just keeps doing it. And you're like, whatever, Word. I'm just going to change this to seconds because it just feels silly with minutes, but it doesn't change the problem. Yeah. What is this? 1997, and it's taking us over an hour to download a file. What are we downloading? True story. Dial-up internet was a thing. Is that Jaden?
I just texted this kid.
Look at this guy walking in.
That's a nice one.
All right. So letter C says F is the rate in millibytes per second. Oh, actually, sure enough, I did need to change that because I have second on 1 and T minutes. They should match. That the file is downloading T seconds after the file has started to download. The variable A equals 60. Yep, that is good. So what do I find out when I do the integral function there? Yeah, how many megabytes you downloaded? The number of megabytes downloaded.
I just don't spot back
But we need a little bit more because we need to explain the limits of this integral. So was it from the beginning?
No. After it starts. Yeah.
After 60 seconds, because it's not like that's what the variable T is, but it's A that's really controlling what we're writing here. You have this packet. The number of megabytes downloaded from 60 seconds. Yep. Oh, you don't have it because you walked in empty-handed. That's right. 60 seconds after the file started downloading to the time represented by X, not from. To the time. Yeah. So again, same deal here. Because that A is 60, if you said that this is the total number of megabytes downloaded by time X, by the time represented by X, you'd actually be incorrect because this is only telling us the extra megabytes downloaded after the first minute, right? You would have to need to know to figure out the total amount of the file downloaded. You would need to know those first 60 seconds and add them back on. So, there's little details here that you've got to be careful with. And then letter B, you guys write something down for that. See what you come up with. That one was a little bit easier. Again, this time because that A was equal to 0 and kind of just built into it, like nobody was infected before the first case. Maybe there's an argument that I should write that a little bit better. But again, this isn't, the idea is what you're thinking. Now, this is more of what you need to think of it as than them asking you to write this down. Because I said the first case was reported. Who's to say that there weren't people infected? X days, because the function is f of x. The variable that you're plugging in is x. This function, yeah, go ahead. Maybe the problem should change to x days as well. Yeah. Yep. No, the problem should also say x days. So there's where the mistake is. Good point, though. That one I did not catch this morning, so that one I still need to fix. Cool. All righty. So yeah, there probably is an argument there that I should really be saying the number of people infected from the time the first person was reported until X days. Because maybe people had it, it just wasn't reported. But again, I said it, but I'm not changing it. Especially because we only have 10 minutes left. Example 2, same thing, particle motion. We will have the beginning of F. One of the changes I made for this one is I'm going to put particle motion at the beginning of F, so we have some time to digest it before we get to the test. But I do want to introduce it here because it goes right along with what we're saying. A particle with position function x of t is already moving on the x-axis when a timer begins at t equals 0. So if you're wondering why we have a velocity at negative times, it's because we were late hitting our timer. We were, looks like 4 seconds late hitting the timer. The graph to the right represents the velocity of the particle. Interpret the following. Oh, I pulled that out too. Just let d of x equal the accumulation function from 0 to x of v of t. Let d of x be the accumulation function, which is the integral of 0 to x of v of t dt. When I integrate the velocity, which is the, I didn't give you units here, the meters per second, the miles per hour, what do I figure out? Definitely not. The same question as we were doing up here. If I am integrating miles per hour, meters per second, what am I finding? V of t is along the lines of speed, so it's definitely not going to find velocity. I know. So in each of the examples above, we had a rate. It was people per hour, and then when we integrated, we got the people. Here, it was megabytes per second, and we integrated, and we got the megabytes. Yeah, so it's getting us distance. And what we're going to do in particle motion is we're actually not going to use the word distance, but we're going to use displacement because we're talking about signed distance, positive meaning to the right, negative meaning to the left. So that's why I used the letter D when I wrote this function, because that D stands for displacement. Okay, I missed it then, sorry, yeah. So it's the displacement of the particle. Again.
I left it at Brandon's house, and the only difference was that my license was facing the direction.
The displacement of the particle from time t equals 0 to the time t equals x. So that's what d of x does. You plug in a value for x, and it tells you the displacement of the particle from time t equals 0. So what we want to do in letter B, and this is actually a review, it's just different notation, we want to find the d of 5 and the d of negative 4. So the d of 5, and this is all an accumulation function is, d of 5 is just an integral. It is the integral from 0 to 5 of v of t dt. And if I have a graph of v, what do I do to figure out that integral? You would think that would be the answer. How am I going to get this value of the integral of v of t dt? Yeah, find the areas. So the displacement is going to be from 0 to 5. We've got this rectangle here. We've got this triangle here. We've got this triangle here. And we've got this triangle here. They're all relatively easy. This guy is 3. Both of these triangles are 1/2. And this one is 1. They are, yeah. And then, those are the absolute values of the areas, but we do have to do a -1/2 and a -1 there. So we end up with 3 plus 1/2, then -1/2, and then -1, which is 2. The particle is 2 units to the right of where it was at time t = 0. Again, it's really specific, you know what I mean? Not from where it began, because it began all the way back at -4. I also made a little more room for this problem in the updated copy when I was struggling to fit everything in here because I asked for 2 things here. This one I think is important, the d of -4, but I also think it helps to make sense of what we're doing, why we're going to, why we do what we do when we move backwards on the graph. So the d of -4 is the integral from -4 to 5 of v of t dt. That area is easy to find.
I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
I have that. Actually, wait a minute. Do I have? It's not -4 to 5. It's 0 to -4, right? Yeah. Sorry. Yeah. What is that answer?
Isn't it?
It's not. It's because look, by the definition of the function, it's 0 to whatever I'm plugging in. So what's the answer? -10. The particle, if we had started the timer when we should have, the particle would have started here. This would have been t = 0, and it would travel 10 units to the right in the first 4 seconds. But what we're solving is the other way around. If I went back in time 4 seconds, where would my particle be from time t = 0? And that would be 10 units to the left. So we really are thinking about going back in time when we integrate to the left. So 4 seconds before we started the timer. The particle was 4 units to the left. Thank you. 10 units to the left. Of where it was at time t = 0. Where it is at time t = 0. Something like that. Yeah. All right, that's where we will pick up on Monday. We'll kind of review that, but that's the next page. So I guess the colored pencils, I should have known we wouldn't have time. So yeah, put the colored pencils back. That's a good idea. It's a terrible spot to have it Friday at the end of class when everybody just wants to put their colored pencils back. But this really, if you understand why that's -10 and not +10, because you're going back in time, it really solidifies why it is that we do that. All right.